morning. Welcome to the 34th lecture on economics, management and entrepreneurship. In our last lecture, we discussed about product development. In particular, we discussed about the differences between products and services. We talked about different phases of product life cycle, and also we discussed about features of product design and value engineering. Today, we shall discuss on forecasting. If you recall, in one of our earlier lectures, we had devoted a full session on demand forecasting. At that time, we had discussed at length on various qualitative methods, and we had given only a glimpse of various quantitative methods. Today, we would like to revisit the forecasting methods, and in particular, we shall discuss about two important quantitative methods, one for intermediate range forecasting, which is regression analysis, or also called multiple regression analysis, which is a part of the broader econometric models, and also we shall consider time series based forecasting, which is usually used for short term forecasting. With the knowledge on these two important forecasting methods, it will be easy for us to use these methods to estimate forecasts of demand, and then use these forecasts for different decisions such as plant location decisions, capacity requirement decision, machine requirement decisions, and of course, production planning and inventory control decisions. So, today's lecture is titled Forecasting Revisited. Forecasting Revisited is the title of today's lecture. First of all, let us recall that to forecast is to make the best estimate of the value of a variable at a future point of time. Then naturally, any estimate is always associated with error. That means, there is an error, there will be always an error between the estimate or the forecast made at a particular time in the future and the actual value of a variable at that point of time. This difference is usually called the forecasting error. The accuracy of a forecasting method is judged by the quantum of forecasting error not at one point of time, but at different points of time. Therefore, different criteria are used to judge the best forecasting method, and normally the best forecasting method is chosen to minimize the mean absolute deviation or the mean absolute forecasting error or mean square error or similar such criterion, which basically gives which is a function of forecasting errors at different points of time in the future at future points of time. Now, it must be also remembered at this point of time that usefulness of a forecast is more important than accuracy. The reason is this, that if we know that a situation in the future is going to be very bad, somebody makes a forecast, we take preemptive actions to prevent the occurrence of such an event. So, naturally in such a case the forecast is not accurate, but it was highly useful. It is a self defeating type of a situation where a forecast is very useful, but is not accurate. On the other hand, there are situations where we make a forecast at a future point of time, and then let us say capacity requirement decisions are made on the basis of future projections of demand. If this projection is made, then the company tries its best to augment its capacity, and also it produces and aligns its marketing forces such that it is able to utilize the capacity fully and sell the amount that was projected in the market. Now, this is a case of self fulfilling forecast. In any case, a forecast is judged not so much for its accuracy, but for its usefulness in taking decisions to improve the situation or to avert a bad future. Now, so in any case a forecast is basically a piece of information, and every information has got a value, and a decision is sometimes defined as an information converter. A decision is made on the basis of information. A forecast is a piece of information, and that is an input to taking decisions. Since forecasts can be or are associated with errors, forecasting errors, usually three types of forecasts are made. One is optimistic forecast, 2 the most likely forecast, 3 the pessimistic forecast. Forecast horizon times and forecasting methods are usually related. As we had discussed earlier, for the long term horizon forecast horizon time, we use qualitative methods depending on the judgment of informed individuals, and we already know of various methods such as Delphi methods, market survey methods, and we can also use historical analogy in which one product has gone through a product life cycle and another product of the same type is expected to go through similar life cycle variations or stages. That is historical analogy and life cycle analysis. Intermediate term forecasting methods are usually cause effect based, and there are different types of methods. One, single equation methods, they are normally known as regression methods, and there can be multiple equations. So, econometric models are basically generalized models of regression analysis, and there are methods that are short term, that are useful in the short term, and they constitute the various time series methods. Today, we shall discuss mostly about the regression methods and the time series methods. First, the regression methods or the analysis that are useful or that are made, that is made for regression methods. So, what is regression analysis? It is concerned with the study of dependence of one variable, which is normally called the dependent variable, on various independent or explanatory variables. In regression analysis, we deal with statistical relationships among random or stochastic variables that have probability distributions. So, we deal with statistical relationships. Regression is not same as causation. A statistical relationship in itself does not logically imply causation. Regression is related to correlation, but they are different concepts. Correlation deals with two variables, treat both variables as stochastic and finds linear relationship or association between them. It is also symmetric in the sense that if A is correlated with B, then B is correlated with A. So, in that sense it is symmetric. Therefore, a correlation is always between two variables and it is symmetric, and this always or usually discussed in the context of linear association between two variables. Regression analysis, on the other hand, can deal with more than two variables. It uses the dependent variable as stochastic and explanatory variables as fixed and finds out a stochastic relationship between them. It is also not symmetric, it is asymmetric in the sense that if A is explained by B, it is not same as B explained by A. So, these are the differences. Now, for both regression analysis and time series analysis, they depend on data. Regression can be done on time series data, on cross sectional data, on panel data and pooled data. Now, what are they? Time series data is basically one variable or more than one variables at whose values are known at different points of time. This is time series data. Cross sectional data is at the same point of time, many variables values are known for various subjects. Pooled data is cross sectional data over a short span of time, and panel data is a special form of pooled data where cross sectional units are observed over a longer span of time. Regression analysis can be done on each type of data. We shall, however, discuss only the regression analysis done on cross sectional data, meaning that the values of the variable at a particular time are collected for different subjects. Regression of a variable y on x, y is the dependent variable and x is the independent variable, leads to what is known as the regression line and is given by the linear equation E y given x equals beta 0 plus beta 1 x. It is a linear relationship, x is the independent variable and y, it depends on x and y is a dependent variable and x is independent variable. Beta 0 and beta 1 are regression, this is regression parameters, not coefficients, they are regression parameters. Beta 0 is the intercept and beta 1 the slope coefficient. Usually beta 0 and beta 1 are unknown and are to be estimated given the different values of y and x for different subjects at a particular point of time. Now, we normally deal with equations that are linear in parameters. What does it mean? It means that our unknown variables are beta 0 and beta 1, unknown parameters whose values we would like to estimate. Therefore, if we have a relationship such as this, although this contains xi square, it is actually a numerical data. Y is also a numerical data. Therefore, the only unknown quantities are beta 0 and beta 1. Thus, it is linear in parameter. Whereas, if we have a relationship such as this, where beta 1 appears here as an exponent of the data. Remember that although we use x for an unknown quantity usually for a variable, but actually it is a value of a variable in numerical quantity. It is a numerical quantity such as 5, 10, 15, 20, etc. That raised to the power beta 1, obviously the relationship is not linear, it is non-linear. If you take log, then it becomes ln beta 0 plus beta 1 ln xi. This of course becomes ln. If you consider this as a variable and this is 1, therefore, this then becomes a linear relationship. This depicts a linear relationships. This is usually called a log linear relationship. Normally, we add a random noise here, a disturbance factor for every individual I, for every subject I or every cross sectional unit I. It will be the population relationship, that is beta 0 plus beta 1 x I plus there will be a random error. This is the stochastic error term. Beta 0 plus beta 1 x I constitutes the systematic or the deterministic component, and epsilon I is the random or the non-systematic component, and I is for every cross sectional unit I or the subject I. Once again, suppose that we have a relationship of this type, this is still linear in parameters, and if the relationship is this type, by taking log it is linear in parameter. And for an individual cross sectional unit, it is this. Now, it can be shown in a graphical form. This is our sample regression function, the linear function, the systematic relationship between y and x or the deterministic relationship, but for every cross sectional unit or subject 1, 2, 3, 4, 5 and 6, the actual values are different. Therefore, this and this is due to the error that is attributable to this particular unit. This is the error for the third unit, this is the error for the fourth unit, fifth unit, sixth unit. And if we can estimate the values of the parameters, call them beta 1 estimate and beta 2 estimate, then this relationship that does not contain the error term gives the value of y I that lies on the line SRF, plus this error term will give the actual value. Therefore, y I hat is basically a point that just falls on SRF line and is just below the actual value line. That means, it is somewhere here. For the fourth one, it is somewhere here, fifth it is here, sixth it is here. Now, let us go for determining how the regression parameters are actually estimated. Let y be the response variable or the dependent variable. x1, x2, xk, I am now considering more than one independent variable. I am considering k independent variables. So, k independent variables and one dependent or response variable. So, the regression model is y as a function of all this plus an epsilon term, and when written down in the expanded form, it is written as y equals beta 0 plus beta 1 x 1 etcetera beta k x k plus epsilon, where beta 0 is the intercept, beta 1, beta 2, beta k are the regression coefficients, and y is the value of the dependent variable. Betas are called the partial regression coefficients. They measure the expected change in y for a unit change in x j when all other variables are held constant. And epsilon is an error term that indicates the influence of other independent variables that have been ignored while making the model. Now, we can have complex multiple linear regression models. Suppose we have an equation such as this, beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 1 2 x 1 x 2. So, even though it is written x 1 x 2, but basically x 1 and x 2 are numerical values. Therefore, the product is also a numerical value. So, this can be written as x 3, where x 3 is equal to x 1 x 2, that can be found out given the values of x 1 and x 2. Therefore, this is equivalent to another equation, where beta 3 is nothing but beta 1 2 and x 3 is equal to x 1 x 2. Similarly, if we have an equation such as this containing x 1 square terms and x 2 square terms, we can write x 1 square as equal to x 3 and x 2 square as equal to x 4. Then this becomes a linear form. Therefore, although we can have situations where we have in variables the relationship could be nonlinear, it can be transformed into relationships or equations that are linear in parameter. So, basically we are taking up cases that are linear in parameter. Now, what we normally do is to estimate the values of the regression parameters by minimizing the least square errors. Let there be n observations. If k is the number of independent variables, then n should be larger than or higher than or more than the number of variables of x j and y. X I j be the value of the ith observation of x j, j equal to 1 to k, and y I be the corresponding value of the ith observation of y. So, we write y I equals beta 0 plus beta 1 x I 1 plus beta 2 x I 2. That means, for the ith observation we have the values of x 1, x 2, x k etcetera and also y. And normally epsilon, the random error component, is defined as normally distributed, independent, normally and independently distributed with 0 mean and constant variance sigma square. This is a symbolic notation of for variation, stochastic variation of the noise component epsilon. Normally and independently distributed random variable with 0 mean and variance sigma square. And since we have many observations, it is possible to convert it into a vector matrix form. We can now write, we had y 1, y 2, y 3 etcetera. We can write y as a vector of all the observations of the dependent variable. Since there are n number of observations, it will be n by 1 column vector. X can be a matrix n by p, where p equals 1 plus k. Beta is a column vector of coefficients with dimension p by 1, where p is equal to 1 plus k, and epsilon is a vector of random errors. This will be clear from this table. These are the variables, y the dependent variable and x 1, x 2, x k are the independent variables. Not we have n different observations or n different cross sectional units or n subjects. For every subject, the values are collected at a particular point of time. Let for the first cross sectional unit, the values are this, for the second the values are this, and for the nth cross sectional unit the values are this. So, what I am now saying is that these constitute a column vector y, and this and a one vector will constitute the matrix capital X. Now, this is shown here. Y is the column vector of the dependent variables, beta is the column vector for all the regression parameters. As you know, there are k number of variables and therefore, associated number of parameters are k in number, but there is an intercept beta 0. Therefore, it becomes k plus 1. That k plus 1 is written as p. So, it is given a notation p by 1. So, it is a p by 1 column vector, and epsilon is also n by 1. There are n number of cross sectional units. This 1 comes here because of beta 0. So, if you multiply x with b, then you will get back y 1 is equal to beta 0 plus beta 1 x 1 1 etcetera. There is one mistake here, this should have been x I k and not, this should have been x I k. Yes. So, what I basically said, that we collect data on the independent variables x 1 through x k and on the dependent variable y for each of the n cross sectional units. And then we have various equations, y 1 equal to beta 0 1 plus beta 1 x 1 1 plus beta 2 x 1 2 etcetera. Now, this I can now put in the matrix form, which I am sorry, yes, in the matrix form such as this, where this is a vector, this is a matrix, this is another vector, this is another vector with these dimensions. The problem is to find the vector of least square estimators. This should come here. The problem is to find the vector of least square estimators, call them beta hat, that minimizes the sum of the squares of the forecasting or the random errors, epsilon I square I equal to 1 to n, and that is nothing but epsilon transposed epsilon. What is this? This is y minus x beta transposed. Now, this will lead to y transposed y, etc. From here, without going through the derivation, we can finally get the estimate for beta, and the estimate for beta is, it is x transposed x inverse x transposed y. X is basically the, if you recall, x is this particular with ones in its first column, and the data that we had collected for every cross sectional units, independent variables are here. So, this is the final expression for beta hat, x transposed x inverse x transposed y. Now, that we know beta hat, we can find out y hat, the estimate of y, it is equal to x into beta hat. Now, we know the actual value of y at a particular point of time, and we have estimated the value of y, and therefore, we can find out the residual. We normally call this as residual E. Now, this is a graphic representation of what I was trying to say for a case when it is a single or a simple regression with one independent variable x, one dependent variable y. This is the SRF, sample regression function, and these are the errors or the residual E 1 and through E 8. And by the way, a point lying here is the estimated value of y for this value of x. For this value of x, the estimated value of E is this. So, basically this line is y hat line, and the actual value is here, the difference is the residual E I. Now, we can find out the error sum of squares. It is the actual value of y minus the estimated value of y, that is y hat I. Square them, sum over I is equal to n, 1 to n. This is nothing but E I square, and this can be written as E transpose D if E is a vector, and then we can find an expression. The total sum of squares can be found out in this manner, and through regression the sum of squares will be total sum of squares minus the error sum of squares. From here, we define a coefficient of multiple determination R square, which is regression sum of squares by total sum of squares. Well, regression modeling is mathematically quite complex. We did not want to go into the details of the mathematical details. Basically, what I want to tell here is that for different cross sectional units or subjects, we observe values of the independent variables and the dependent variables. Dependent variable is y, independent variables are x 1, x 2, x k, and then we find out the equation of the regression line. It is a linear regression. By estimating the best values of regression parameters beta 0, beta 1 up to beta k, that minimizes the regression errors, mean square errors or squared error. It is called a least square estimation. It is given by, in the vector matrix form, we can write y vector is equal to x beta plus epsilon, and we can find out beta as x transposed x inverse x transposed y. That is the expression for beta. Once beta's estimate is known, we can find out, we can make the estimate of y at different values of x by using the relationship y hat equals x beta hat. Then we can find the difference of the actual value of y and the estimated value y hat. We call it error. Given the error, we can find out three types of errors, three types of sum of squares: error sum of squares, total sum of squares, and regression sum of squares. The ratio of regression sum of squares to the total sum of squares tells us how much our regression equation explains the variation. That is called SSR by SST. The explained how much SSR is the error sum of squares defined by or explained by our regression model, but the actual sum of squares is SST, the total sum of squares. Normally, we go for an adjusted R square statistic, because sometimes we are not very sure as to which variables influence the value of y, which independent variables. The choice of the variables, independent variables, is sometimes quite challenging. One may take many large number of variables to explain y. It has been seen that quite often many of them are not important, many of them are related with each other, and they can increase the explained sum of squares, that means R square value. So, R square does not always indicate the adequacy of a regression model. It has to be adjusted for because of redundant or near redundant explanatory variables being included. That is why it is given by 1 minus error sum of squares divided by n minus p and divided by total sum of squares divided by n minus 1. Once again, R square or adjusted R square are good indicators of the extent to which the errors are explained by the regression line. We also use t statistics to find whether a particular beta is significantly different from 0. We are, this is beyond the scope to discuss how t statistics are calculated, but basically there are, what I want to say is that there are quite a large number of software packages that deal with regression modeling or regression analysis. If you can define the variables, independent variables x 1 through x k and independent variable y and give their values for different cross sectional units, then it will make the calculations for yourself. The software package will make the computations for yourself and for you, and then define the R square values, find the R square values and find the t statistics, and also do a lot of other things. So, we should know the meaning of these statistics rather than how to derive them. So, if for example, what I want to say is that suppose by regression modeling I get a model such as this 20.50 plus 0.1 x 1 minus 8.2 x 2 plus 2.5 x 3. Now, these are the estimated values. This is estimated value of beta 0, this is estimated value of beta 1, estimated value of beta 2 and of beta 3. These are the estimated values that came out of our equation, which was beta 0 beta estimate equals x transposed x inverse x transposed y. Now, look at the values 8, 2.5, 20.5 and 0.1. Now, this 0.1 appears to be very small. The contribution of x 1 to the change in y seems to be quite less. T statistics say whether this 0.1 is close to 0.0, close to 0, or whether this is close to 0, this is close to 0. Now, normally there are tests of hypothesis with the method of which we can find out whether each of these coefficients are different from 0. Looking at it, it appears as though 0.1 is too small compared to these two, and probably it can be considered that the effect of x 1 is very negligible, and therefore, we can straight away neglect this. We can say that the equation y hat is equal to 20.5 minus 8.2 x 1 x 2 plus 2.5 x 3. So, t statistics help to find out whether the coefficient is significantly different from 0 at what level of significance. And then as I said, R square value gives us R square equal to let us say 0.9 tells us that 90% of the variation in y is explained by these three factors. Whereas, if the R square value would have been only 0.45, it would have meant that only 45% of the variation in the value of y is explained by the regression equation. So, this is the connotation of these two statistics. Instead of writing R square as I told you, we should normally go for some sort of an adjustment to indicate how far redundant variables have been added to our list of independent variables. Now, after we do all this, we also go for residual plots. If you remember, we calculate for each cross sectional unit I, we calculate E I, the residual, y I minus y I hat. This is the value of y I that we calculate from our regression equation, and this is the actual value. Now that we have the residuals with us, these residuals are actually surrogate measures of epsilon I. Epsilon I is the noise which we assumed to be normally distributed with 0 mean and constant variance sigma square. This was our original assumption when we derived the betas. Therefore, now is the time to actually judge whether these assumptions are actually justified. This justification can be examined only by analyzing the residuals E I. So, what we do, there are different forms of analysis of the residuals. They are called residual analysis. Residual analysis. A regression model is incomplete unless a residual analysis is also made. Now, residual analysis normally takes different forms. We have discussed here, we have only indicated here different plots, residual plots. One is the normal probability plot of the residuals, because we had assumed the residuals, the errors to be normally distributed, the residuals should also be normally distributed. Then the residuals versus the predicted values of the response variable should not show a pattern, and residuals versus values of each regression variable x j should also not show any pattern. Let me expand this. Suppose that we have residuals E I equals 1 through we have n number of observations. We can now plot E I as a histogram or as a cumulative distribution function. As you know, a normal probability continuous normal function, normal density function looks like this, and when we can draw a cumulative distribution function that goes up like this from 0 and become 1. This from minus infinity to plus infinity, this also goes to plus infinity to minus infinity, but the area is added up, that is why it is always rising. This is called a cumulative distribution function. Now, if this axis is properly scaled, then it is possible that this curve looks like a straight line. If it is properly scaled, if this axis is properly scaled, this varies from 0 to 1, but it is properly scaled. So, we can say that this is the ideal normal curve, normal CDF, normal curve, and our actual EI when plotted in this manner may actually look like this. Now, this extent of deviation from this is normal and this is actual indicates to what extent the normality assumption is deviated in the data. So, this normal probability plot basically is done in this manner. The second type of plot that is required for residual analysis is plot of residuals versus the predicted values y bar for different I. So, this is observation number 1, number 2, number 3 and like that 8 or 10 observations. The errors, some will be positive, some will be negative. Let us say that the values are like this. Now, you can see that there is a pattern, or that you may normally, if there is a relationship, normally it will show a pattern such as this, increasing pattern. There is also a pattern here. There is a cyclic variation or a seasonal variation here, and there is a diverging pattern of relationship between E I and Y I hat. Both indicate that it is not random, that there is a relationship and that variance sigma square is not constant in this case. It is a function of y I hat. The third plot is the plot of residuals versus each regressor x I. Now, here you will have for each regressor x 1 and x 2 and x 3, you may see all the points lying here. There are so many observations. For this it may be here, for the third you may see it here. So, basically the deviation would indicate how far E I depends on x I, x. So, these are the different ways by which the normality is judged, the independence is judged and the constant variance assumption is judged. So, friends, I discussed a full session on regression analysis, because regression analysis is quite useful in making demand forecasting, particularly for a new entrepreneur who has had not much of a past data. If past data were available, a time series forecasting method could have been used. Instead, for a new entrepreneur, he can make assumption regarding demand of a product on the basis of various economic variables such as GNP, population and so on and so forth. For such a situation, the most adequate forecasting model is the regression model. In our next class, we shall take an example and of regression model and then use or expose you to the time series forecasting methods. Thank you.